So today I'm going to start a new lecture, and this is the beginning of chapter 6 of my book, and we are going to cover response surface methods. So this chapter will basically focus on response surfaces, and I'm Dr. Ranjan Ganguly. Now, if you have been studying any kind of scientific field or engineering field, you know that we spend a lot of time on developing models. And models are mathematical abstractions which are used to simulate the behavior of a real system. Now, essentially, there are two things you can do in scientific pursuit. You can do experiments or you can do modeling. And essentially, as systems become very complicated, it's very expensive to perform experiments, and therefore you need to do modeling. Therefore, modeling has become very important and models have become very useful. The second important aspect of modeling is that models let you do parametric studies, sensitivity analysis, and optimization. And this is not something which is possible by doing experiments. So again, before you really prototype any system or you make any system or manufacture it, it's always good to do modeling and optimization. Now, typically models use some kind of mathematical equations, and these equations are often very complex. You need to do computer solution of these equations, which are typically partial differential equations. You will have various conditions placed on these equations, such as initial and boundary conditions and so on. Now, at the end of this enormous exercise in modeling, still whatever you get is not the actual behavior of the real system, but it is a close approximation of the behavior of the real system. But in many cases, this particular behavior which you get, which is close enough to the real system, is sufficient for most design problems, as long as you capture the behavior of these system parameters with respect to the design variables in a proper manner. Now, one of the things which has happened in modeling is that there has been a growth in the power of computers, an enormous development in the field known as computational science, which includes not just fields such as gas turbines, steam turbines, and so on, but also you could model viruses, the liver, heart, and many such systems. So computational science is now a very important field, and it is used to create even new drugs and medication. Now, in all these cases, at the end of all this mathematics, you have a simulation code of the physical phenomena, and these codes are typically large and complex. And it's very difficult to link the optimization procedures which are developed to these simulation codes. In many situations, you may have proprietary simulation codes, or you may have codes which have been developed by companies, and therefore you do not have access to a lot of the features inside the code. So linking these computer programs is quite difficult. And if you have dabbled with linking computer programs, you know that this is a very cumbersome task. So one of the ways to handle this problem of linking optimization software with the computational software is to create a model of a model. And essentially, this is known as a surrogate model or also Metamodel. Now, once you have developed these Metamodels, these are relatively simple to use with the different optimization methods we have discussed before. And this process of using surrogate model decouples the computational problem or the modeling problem and the optimization problem. And again, this has become popular because it lets us facilitate the spread of optimization method in the various companies where it is primarily targeted to use. So again, these models are known as surrogate or metamodels. So we will primarily use the word metamodel here. So a metamodel is formally defined as a model of a model. So for example, let's consider a typical scenario in modeling where you have a computational software. You have a design variable vector x coming into the computational software, and out of this computational software you are getting your cost function and the constraint functions. So this is a typical scenario which is there when you are trying to use optimization methods on any real system. Now what you do is that you replace this computational software by this so-called meta model. And essentially in the meta model, if you feed this vector x, it also gives you values of f, h, and g, but these are not the exact values which you get from your computational code most of the time, but are very close to those values. So we use this term hat. So you are seeing here f, a hat on top, same with h and g, and these are basically predictions obtained from the meta model. Now essentially the closer your meta model is to your computational model, the better it is, and then instead of using this computational program, you can simply use your meta model for the optimization problems you are trying to do. So we have seen that typically computational programs are developed using physics-based models, and physics-based models essentially use partial differential equations which govern the problem, and then you solve these equations with various initial and boundary conditions. Whereas a meta model is actually a mathematical model or approximation of this computer program. So the meta model is purely mathematical, and essentially mathematical functions are used to form the meta model. Most popular would be polynomials, which are used in the response surface methods. You could also use sigmoid functions, radial basis functions, trigonometric functions, neural networks, and so on. But essentially the simplest possible functions in mathematics are polynomials, and therefore response surfaces which use polynomials are quite easy to use, and they are also quite robust and good as far as results are concerned in most cases. So response surfaces are polynomial functions of the computational analysis which you have developed. So essentially you take your code and you replace your code with these functions f hat, h hat, and g hat being the predictions of your meta model. So I would say that response surfaces are some of the most widely used meta models as far as optimization is concerned. And a good meta model would provide you with very good quality of functions here, and therefore the optimization results you will get will be quite good. So now we look at the concept of response surface methods formally. Response surface methods are a collection of statistical and mathematical techniques, and they were created to develop, improve, and optimize products and processes. And most of these came from the industry where testing was required, where quality issues were required, and so on. So essentially the fact is that in many cases you have a number of input variables, and there is some performance measure or quality characteristic, and essentially you need to generate a functional relationship between these performance measures or quality characteristics and the input variables. So this is where the response surface methods come in, and this field was developed by many people, and there is a very good book, Response Surface Methodology, by Montgomery and Myers, who lay out much of the theory in this field. Now this performance measure or quality characteristic used in response surfaces is typically called a response, and it is a function of the different input variables which you have. Now these relationships are typically found by tests or experiments, and therefore there is a close relationship between the field known as design of experiments or DOE and response surface methods. We will discuss DOE in detail in subsequent lectures. Now, response surface methods are linked to quality control since quality metrics can be used as response. Now, whenever we plot the response in terms of the input, we actually see a pictorial view of a response surface, which can be plotted graphically if you have 2 inputs or 3 inputs at maximum. And of course, these response surfaces are there computationally if you express them in mathematical format. Now, essentially, these response surface methods concern themselves with product or process improvement. They were often widely used in the chemical fields, and now they are also used widely in optimization, and so they are known as response surface methods. So now let's come to the functional description. Essentially, response surface method seeks to find a functional description between the variable y and the set of input variables xi1 to xk, and there is some discrepancy between this function and the real representation, and that we denote by this term. Now, this term is a statistical variable, and therefore you can consider it to have zero mean and variance sigma square, where sigma is the standard deviation. So that's essentially what the response surface method does, is that it tries to find this function. And of course, at a very general level, this would be a surrogate model or a metamodel. It becomes a response surface when you look at polynomial approximations of this function. So these particular variables are known as natural design variables, and they are often used in terms of measurement with actual units such as meters, etc. So for example, we could have the height of k people here, and then these would be natural design variable. Or they could be something like one could be height, one could be weight, and some different parameters such as those. Now, instead of using n for the number of design variables, we typically use k in this chapter because that has been the widely used convention in the response surface literature. So essentially, we will use xi1, xi2 to xk as the natural design variables for the problem. Now, in the response surface literature, we typically convert these natural variables to something known as the coded variables. So these are x1, x2 to xk, and this is done through a linear transformation. So essentially, coded variables are a normalized form of the natural variable, and each of these coded variables has a range from -1 to 1 for its low and high values. So let us think of one of the variables as being height. Now, a person's height could range from a low of maybe 0 in a theoretical sense to a high of 6 feet, 6 inch or 7 feet. And those would be the natural variables for this design variable xi1. Now, in x1, we essentially use the bounds -1 to 1. So -1 is the lowest possible value, which could be 0. We could make the 1 as maybe 10 feet, and then we would normalize this height into this particular domain. So this lets us use many of the factorial designs in the design of experiment we will discuss later. Now, in response surface, from what we know about calculus and mathematics, the first function which would come to mind would be to use polynomials. And essentially, when you use polynomials, you want to use the lowest polynomials which are possible. So we would at least like to capture the basic slope and curvature of the function and look at the sensitivity of the response to the design variable. So again, this is the functional form expressed now in terms of coded variables for the response surface, the metamodel, or the surrogate. So first thing which would come to mind is a linear model. Now, this is the simplest possible model, And here you can see that this model would capture the slope of the function using the term beta 1 x1 and beta 2 x2, and also it would capture the mean value of the function through beta 0. So if we have only two design variables, the linear model would have this form here, and there would be these three parameters beta 0, beta 1 and beta 2 which we need to find. Similarly, you extend this to a quadratic type of fit. And here again for k is 2, we have written out this fit here. Now here you see the first three terms would involve a linear model. Then we have put in curvature terms. So x1 square and x2 square are essentially curvature term. And the final term involves x1, x2, which is an interaction term. So this quadratic model would capture a function quite well. And again, recall that we have discussed many times that most nonlinear functions can be modeled by a quadratic function near its particular point. So essentially, when we use a second order response surface model, we are using this fact in mind. And here you can clearly see that you now have these coefficients beta 0, beta 1, beta 2, beta 1, 1, beta 2, 2, beta 1, 2, which you need to calculate. Now, how do we calculate this is the thing we have to look for. So once again, just to extrapolate to k dimensions from 2 dimension, the linear model is given like this. You have x1 to xk terms, and the quadratic model is given like this, which we have written out in summation form. So again, this would be the linear model here, including just the mean value term and the slope terms, and then the curvature term and the interaction terms here. So this model is quite widely used in response surface work, that is the quadratic model. Now, how do we find the betas? Actually, there is a close connection between response surface method and the linear regression. So for example, consider this response surface here. Here the betas are the parameters which you do not know and you need to calculate. So essentially what we need to do is we need to generate data linking y and x at several points in the domain. And once we do that, we get a bunch of equations where x1, x2, xk and y are known, and then the betas can be found using certain least square fit type of situations. So again, this is a field known as regression, and this is a branch of statistics where we use data to estimate these betas. Now, a typical multiple linear regression model with k regression variables would have this form here. So we have the response surface here and we have a error term here epsilon. We then extrapolate it to the quadratic surface. Again, if you look at the quadratic surface here, you may think that these squared terms would cause some problem, but actually these squared terms can be replaced with new variables x3, x4 and x5. And recall that if you have these values x1 and x2, then all these x1, x2, x1 square and all just become numbers. And so essentially I can write my model in this form here, where I have defined these new variables x3, x4 and x5, and then I can calculate all these coefficients based on the data points which I have. So we see that a regression model that is linear in parameters beta is a linear regression model regardless of the shape of the response surface which it manifests. So for example, our quadratic model has this form here where you have all these x1 square, x2 square and x1, x2 terms. And then if we simply redefine those terms, we have this model here. So as far as response surfaces are concerned, they will all become linear in terms of betas. And if we have a set of points which are relating x to y, we can essentially find these betas so as to minimize the epsilon value. And that is going to be the least square method, which we are going to discuss in the next video. So I hope you enjoyed this video, and I will see you in my next video.